All right, we'll start again. Thank you very much, the LOC. It's been a very good job. So, yeah, so I'm Pablo Torne. I'm going to talk today about submillimeter pulsations from a Magnetar 1810 minus 197. And it's a work I have done also in collaboration with colleagues here and also from the East Asian Observatory. So very briefly, some motivation. Why do we want to try this kind of super high radio frequency observations? I think there are two main drivers. Mainly understanding physics of radio emission. How is the radio emission produced? For instance, we have seen examples before with the spectral energy distribution. We can try to fit models, understand what's happening. Maybe some additional components of emission can boost the emission at millimeter or submillimeter wavelengths. So we have to have a look. And even perhaps help to understand a bit the evolutionary paths of neutron stars. You may know that some pulsars behave sometimes a little bit like magnetars, or they transition among modes. So checking if they, for example, are visible at millimeter wavelengths can help to link them. And a second, a bit more exotic case would be to try to observe through regions that are very, very dense and turbulent. For instance, the galactic center, where we know there is a lot of scattering. So if we increase the observing frequency in radio, we decrease the effect. So just briefly, I like a lot this picture, also that's mentioned in the Smith book that I like from the 70s. It's just to show you the typical windows where we see pulsars and study them. It's a radio at centimeter wavelengths or even meter wavelengths now. There is some detections in the infrared and optical and the high energy tech, X-ray and gamma ray. But there is a large gap here, a window between, let's say, 10 gigahertz and 80 gigahertz, where we know almost nothing, or even a bit more connecting to the infrared. And this is just a toy example with the crab pulsar SAD, but you can also have a look at the Danilenko paper for a spectrum of Vela in many wavelengths. You'll see again, we have this gap. And then the idea is to try to cover it and learn a little bit more on the emission mechanism there. One example, this is very basic, but models like the bunched particles predict that we will have some amplification of the emission, but this coherence will at some point decrease in efficiency, and perhaps some incoherent component of emission can take over. And this may imprint in the spectrum a flattening or even a turn up, so a deviation from the typical steep spectrum. And in fact, already in Michael Kramer's thesis in the 90s, when they started doing the first observations at 20, 30, 40 gigahertz of pulsars with Effelsberg, they started seeing in some cases some data points that seem to deviate from this extrapolation of the power law, which could indicate something like this. And another example is the galactic center Magnetar, where we see also a strange effect. The centimeter wavelength seems to decay, and then the millimeter wavelength emission was much brighter. So again, something strange happening or inverted spectra. So it's just an example, phenomenological models, but to give you an idea of what do we try to do when we observe at very, very high frequencies. Now, magnetars, I don't have to tell you much because we have already great talks. They are peculiar, they are rare. One of the most important properties for us is they tend to have a flat radio spectrum or even inverted. So this means they are bright at short millimeter wavelengths. So perfect candidates for this type of observations. And just to show you how important they are, there are 6 pulsars detected above 80 gigahertz and 4 are radio magnetars. So it's, they are really good candidates. Now, despite having a flat radio spectrum and being bright, these kind of observations are still challenging. 2 main reasons. First, the telescope dish size, when you go to millimeter or submillimeter wavelengths, is much smaller than the typical 100-meter class telescope that we are used to in the centimeter. And the system temperature is usually much, much higher because the atmosphere is not transparent. So it's difficult to detect the weak emission. Also, very rapidly, to link with the final results I want to show you on the submillimeter window, we did a bit of a crazy experiment with a new camera that we had at the 30-meter telescope called NICA-2. This is kind of a bolometer, but it uses, for those of you that like the technology stuff, it's a kinetic inductance detector, so it's not exactly a calorimeter. And they offer very large bandwidths, so the sensitivity is kind of high. To give you an idea, 50, 60 gigahertz of instantaneous bandwidth. Right? So we were doing some tests, and because 1810 had a new outburst and it was very active, we thought, well, why don't we try to see if we can detect it with this technology? And one of the key things was to sample very fast, because these kind of receivers or detectors are typically used for imaging. So when I tell the engineers, hey, I want microsecond resolution, they look at me like if I were an idiot. Plus, you say, I only want to use 1 pixel of a camera that has 3,000 pixels. So it's very weird. But they managed to sample very fast the detector, and we managed to see the Magnetar. You can see here the average profiles at 150 and 260 gigahertz, which are the two observing windows of this camera. And even single pulses were detected. So that's fine. And just to show you that this kind of
pulses.
Pardon?
Individual pulses.
Yeah, these are single pulses. So these things are sensitive. The Magnetar, of course, is very bright as well. Flat spectrum, blah, blah. So it worked, right? So this kind of technology can be used to observe pulsars. Then sometime after, I spent some time in Hawaii. I was very lucky to work with the James Clerk Maxwell telescope, and they have another camera called Scuba 2 that is similar. It's not a kinetic inductance detector camera. For those of you that like the technology, it's a transition edge sensor camera, but it's kind of similar. Very large instantaneous bandwidth. And it can observe at 2 windows simultaneously, 350 gigahertz and 660 gigahertz more. So yeah, now within the submillimeter window. So we tried. I told the people, all right, why don't we try to see if this Magnetar is also visible? And without going into too much detail, I give you the reference here for the paper if you want to read more. This telescope is scanning a field of view, very large. So what we were doing, you can see here just a scanning pattern and the detectors that we put behind. And then we are just scanning over the field and with a lookup table, extracting the data from the position of the Magnetar, building a time series, and then folding it with an ephemeris. That was very simplified the methodology. And it worked. So we have here, I hope you can see, although it's a bit difficult. And the first column we showed the phases where we have the on, so the beam pointing towards us, the off when it's not, and then the residual, so the on minus off maps. Thank you. In fact, I hope you can see because it's a bit difficult, but at the very center, if you pay attention, you can see the pulsation, right? So this is, by the way, in the 350 gigahertz window. We did not detect it at the 660 gigahertz window. It was simultaneous observation, but we did not get detections. So there has been some published images of magnetars at submillimeter wavelengths, but not pulsations. So this is the first time we can resolve the pulses. By the way, there were 3 epochs, as you can see, and there is some variability, as I'll show you. So benefits of doing a fast sampling, benefits of being able to resolve the pulses versus just getting an image. But first of all, you get more signal to noise ratio because you are having the energy concentrated on the pulse. When you do an image, you kind of add together all the noise on the off pulse. You can try to detect other things like single pulses, fast transients, fast radio bursts, who knows? But the most important for this work is that you can also infer the size of the emitting region. And if you put together that information with the flux density, you can try to estimate brightness temperatures. And this is interesting for some emission model checks. Just here is the brightest detection, just to show you that we did not only get these beautiful maps, but we could also extract the average pulse profiles. This was not only done with the JCMT. I used as well a collaboration with Effelsberg and the Iran 30-meter. We planned the observations fully simultaneous, but unfortunately, due to weather and so on, they ended up being 1 day apart. And of course, we need to be careful then because magnetars are very variable. But nevertheless, first we wanted just to check, okay, let's check the spectral energy distribution. Is there some flattening, some turn up, as some models predict? Well, we don't see that. And in fact, we see something different. We see a broken power law with a peak at about 140 gigahertz. But again, caveats, careful, because also scintillation here affects the different parts differently. And we have the variability that is intrinsic, and we cannot really correct for it here. And summarizing the results, first, the emission that we see in the submillimeter window seems to be still coherent because the brightness temperatures are around 10 to the 14 Kelvin. And as you may know, to explain emissions with brightness temperature above 10 to the 12 Kelvin is difficult if you don't invoke some kind of coherent mechanism or amplification. We cannot conclude anything on the coherence length, thanks, because we don't see the spectral turn-up, which is what we wanted. In fact, we see something very different, the broken forward law. The submillimeter emission is highly variable. It is like in the lower frequencies, right? This thing changes a factor of a few whenever it wants. And I show you on the right-hand side the pulse morphology from the FSBR observations at around 6 gigahertz all the way up to the 350 gigahertz. And you can see the pulse morphology is very similar. Okay? At FSBR, we see 2 components or maybe 3, but the main one is similar. So we think this supports a similar emission region. Right? So at the end, the submillimeter pulsations we see are kind of similar to those at also the lower frequencies. So we think that first, because we see the pulsations, we can link it with co-rotating magnetosphere as opposed to other models from all bad disks or other emissions, and that it's likely the same emission process producing the submillimeter emission and the lower frequency emission. Of course, only one source. We would need to observe more and have better statistics and better numbers. And just last minute, how can we improve? Because this was an experiment, really. We didn't know if this would work. It was the first time applying all these algorithms. Well, my dream always is to have the multi-wavelength observations of Magnetar fully simultaneous, but it's very difficult. We should try to extend to the infrared and the optical. Maybe we don't see the turn-up because it's at a higher frequency. As you may have seen before, that we know that the infrared and optical emission sometimes is higher than the extrapolation from radio. So something has to be happening there, and it would be fantastic to fully sample it. There is another gap between 10 gigahertz and 60, 70 gigahertz that we may now be able to cover very well, for example, with the band 1 of ALMA that is coming online, plus other telescope. And of course, polarization information will be also great, but this is a bit too complex. This receiver, the one in the JCMT, could in principle do polarization, but not at a very fast sampling mode, so we left that for the future. Of course, other kind of sources. So the main idea, and I more or less leave the summary here and take questions, is, well, we have demonstrated that some other technologies can do these kind of weird observations, and this is very new. So I would just like to say, just think about ideas, because this can have other applications as well. So I'll leave it there. Take questions. Thank you.
No, I mean, that's absolutely incredible stuff. So that's like, please do it. So just it does bear a lot of information for any theoretical aspect of what the radio emission mechanism might be. So just a quick question. So that, do you have any problems with ALMA, or what's the problem? because so just why don't you submit a bunch of ALMA proposals?
Yeah,
and especially now when you show that at least this object will be visible with ALMA, there's no questions.
Or maybe more, right? Because remember, the JCMT I didn't mention, it's a 15 meters dish. So
yes,
imagine with more sensitivity. So main problem with ALMA is to get the time.
Yes.
And unfortunately for pulsars, we are struggling, because we have the impression that the science cases are perhaps not fully understood by this dual anonymous referee process. We have to improve our proposals, that's for sure.
Are you collaborating with theorists on your proposals?
No.
This is really interesting stuff.
Yes.
And it will produce some new results.
Yes, and you know that ALMA has now this phase mode, which allows to resolve the pulsations, which is also what I'm trying to highlight here. The main difference is you can learn much more, or a bit more, from the pulses than the images. So yes, we are trying. So hopefully we'll get eventually time.
Cool.
More questions?
Can you say something from your hyperflexive observations about location of the emission region in Magnetar?
I didn't try, and one of the main issues is that the time sampling you can get with these telescopes is a bit limited, right? So at the end, you don't resolve really well the pulses, and in this case, I must add, the pulses are not aligned via an ephemeris. They are aligned by eye, so no, in this case, we didn't do. If we had a very good ephemeris, phase connected and everything, we follow the data with the same ephemeris, then you would start seeing also maybe offsets in phase, and we can start seeing more.
I mean, with some of the observations at centimeter wavelength, we would get a good ephemeris for that data.
Yes, but we didn't do that. And it was not exactly the same day, but yes, I mean.
Anyone? question?
Yeah, really nice job. I was just curious, could you also do something on the other end of the spectrum, with ultra low, long period magnetars with JCMT?
So in principle, this is a new mode of observations, if you want to call it like this. So I like seeing this a bit like commissioning. Right? We have these ideas both with the Nika 2 camera and with the Scuba 2 cameras. So yes, we could apply for new observations like this. The observing mode is there now, so it's much easier. We had to do tons of tests and several observations until this was, actually the observations were fine, but the algorithms to reduce that, when I told the guys, hey, I want to map every 10 milliseconds, like, and they look at me like I'm an alien. They're not used to this, but it works. And the 30-meter, by the way, has also a heterodyne receiver, which works very well. That one can sample down to 20 microseconds or so, while these kind of cameras, they are in the millisecond scale. So yes, these low pulsars would be now fantastic.